Touch something metal in the room for a moment. The edge of a lamp, a doorknob, a coin, the back of a phone. Almost anything you choose has a small fraction of something inside it that no ordinary star could have made. Not the sun, not the next star over, not any of the bright points you can see in a clear sky tonight. Some of the matter in your room comes from a stranger place than that. Tonight, we're going to find out where. In this video, we will walk through 6 things together. We will look at the limit every star hits when it tries to build heavier matter. We will walk through what is left over when a star finally fails. We will examine a collision so brief it was over before any human noticed it, and so bright it lit up an entire galaxy. We will look at the cloud of gold and platinum and uranium it threw into the dark. We will sit with where that cloud has drifted since, and we will end with what part of it is now sitting on your skin. By the end of tonight, you will understand exactly why the heaviest, rarest matter in your life was forged somewhere the sun could never reach. So settle in, let your shoulders drop, pull something soft over you, and let the lights go low. We're going to take our time tonight. If you enjoy these slow science walks before sleep, a quiet like or subscribe makes a real difference for the channel. I am grateful you are here. Now, let us begin. Start with what you already know about stars, and we will move slowly from there. A star is, at its simplest, a sphere of hot gas that has become massive enough for its own gravity to crush its center until the center begins to fuse. Hydrogen, the lightest and most common element in the universe, gets pressed so hard that its nuclei smash together, and when they do, they release a small amount of energy. That energy is what holds the star up against its own weight. Without that fusion, the gas would simply collapse. Because of that fusion, the star can shine for millions or billions of years. Every star you see at night is doing this. The sun is doing it right now. In its core, 4 hydrogen nuclei combine, by a slow series of steps, to make one helium nucleus, and a tiny amount of mass becomes light. Multiply that by the unimaginable number of fusion events happening every second inside the sun, and you get the warmth on your face on a summer afternoon. The numbers, when you actually let yourself see them, are quietly enormous. Every second, the core of the sun converts about 600 million tons of hydrogen into helium. About 4 million tons of that mass becomes pure energy, streaming outward as light. The sun has been doing this for roughly 4.5 billion years, and it has enough hydrogen left to keep doing it for roughly 5 billion more. That is not a small thing. That is the steady, quiet engine that has made every sunrise on Earth, every photosynthetic leaf, every breath of oxygen, every warm afternoon in human history. But hydrogen does not last forever. Eventually, the star uses up the hydrogen in its core. The core contracts again, gets even hotter, and starts fusing helium into carbon. When the helium runs out, if the star is heavy enough, it fuses carbon into neon, then neon into oxygen, then oxygen into silicon, then silicon into iron. This is the part that gets called nucleosynthesis, the building of the elements. Every atom of carbon in your body was assembled inside a star by gravity and pressure. Every atom of oxygen in the air around you came from a star. The calcium in your bones, the nitrogen in the proteins keeping you alive, the iron in your blood that lets it carry oxygen, all of it was made the same way. Cook hydrogen long enough, and you get a periodic table. This is the famous line you may have heard before. We are made of star stuff. It is true, and it is beautiful, and it is most of the story. But it is not the whole story, because somewhere in that climb up the periodic table, the star runs out of room, and then the periodic table runs out of room. To see what goes wrong, picture the inside of a massive star late in its life, just before the end. The core of the star is a layered structure, almost like an onion. The outer layers are still fusing lighter elements. The deeper layers are fusing heavier ones. Hydrogen on the outside, helium under that, then carbon, then neon, then oxygen, then silicon. And right at the center, after all of that, sits a small ball of iron. Iron is where the building stops. Stars build elements heavier than hydrogen because fusion releases energy. 2 small nuclei come together, and the resulting nucleus is slightly less heavy than the sum of its parts. The leftover mass becomes light, and that light is what powers the star. As long as fusion releases more energy than it costs to make happen, the star keeps shining. But this only works up to a certain point on the periodic table. When you fuse two iron nuclei together, you do not get net energy out. You have to put energy in. Iron has the most stable nuclear structure of any common element. To break it open, or to fuse it into something heavier, costs the universe a debt it cannot pay from inside a stellar core. The fusion that has been holding the star up for millions of years suddenly stops paying. The core, which had been propped up by the heat of fusion, can no longer hold itself open. In a fraction of a second, the iron core collapses, and in the chaos that follows, the outer layers of the star bounce off the collapsing core and explode outward. This is called a core collapse supernova. It is one of the most energetic events in the universe. For a few weeks, a single dying star can outshine the entire galaxy it lives in. Inside that explosion, in the heat and pressure of the supernova shockwave, some heavier elements do get made. Copper, zinc, a little bit of silver. The shockwave can briefly create the conditions to push past the iron wall, and a small selection of heavier atoms get fused on the way out. But it is not enough, because there's a long list of elements heavier than iron in this universe, and supernovae alone cannot account for them. Gold, platinum, uranium, the lanthanides, almost everything in the lower half of the periodic table. Where did all of that come from? For about 60 years, this was an open question. Iron is the wall. To understand why this question was so stubborn, we need to talk about how nuclei are actually built. Imagine a small workshop inside a star. The materials are atomic nuclei, the tiny dense cores at the center of every atom. Each nucleus has some number of protons, which give it its identity, and some number of neutrons, which give it its weight. Carbon has 6 protons. Oxygen has 8. Iron has 26. Gold, way down the list, has 79. To build a heavier element, the workshop has 2 choices. It can either smash protons in, which is hard because protons repel each other electrically, and you need huge amounts of energy to push them together. Or it can drift neutrons in, which is much easier because neutrons have no electric charge and can be absorbed by a nucleus quietly, without resistance. In ordinary stars, neutrons drift in slowly. A nucleus catches a neutron, sits with it for a while, and then, if the new combination is unstable, the neutron eventually decays into a proton, and the nucleus becomes a slightly heavier element. This slow capture is called the S process, the S standing for slow. It is a real, ongoing thing, and it builds many of the heavier elements in the universe little by little. Strontium, barium, lead. The S process is patient, and it works. But the S process has a limit. It can only build elements up to a certain mass before the chain breaks. Beyond that limit, the slow drip of neutrons is not enough. To get heavier than that, you need a different process entirely. You need to flood a nucleus with so many neutrons, so quickly, that it cannot decay between captures. The nucleus catches a neutron, then catches another one before the first one can decay, then catches another, and another, and another. By the time the storm is over, the nucleus is grossly overloaded with neutrons, and it has to dump that excess in a long cascade of decays. What is left at the end of that cascade is a heavy element, sometimes very heavy. Gold, platinum, uranium. This is the rapid neutron capture process, or R process. They are standing for rapid. The R process is the only way the universe knows to make the heaviest elements. And to run the R process, you need a place that is unimaginably rich in free neutrons, hotter than almost anywhere else in the cosmos, and ready to dump all of that into a small volume of matter for a fraction of a second. That is the recipe. The neutrons do not wait. For most of the 20th century, astronomers had a guess about where the R process happened. They thought it happened inside supernovae. The reasoning was simple, and it almost worked. A supernova is the most energetic event most stars ever go through. It releases huge amounts of light and matter into space. It enriches the galaxy with elements that did not exist before the star died. If anywhere in the universe was going to be a kitchen for the heaviest atoms, surely it would be there. So for decades, textbooks said gold came from supernovae. The image you may have grown up with, of stardust raining down from exploding stars, was the picture in everyone's head. It was a beautiful idea. It was also mostly wrong, because as the math got better, And as observations of distant galaxies got more precise, a problem started to show. There were not enough supernovae. Or more carefully, the supernovae that did happen did not seem to be making enough of the right kinds of heavy elements to explain how much we see around us. Gold, in particular, was a problem. The amount of gold in the universe, in old stars, in the dust of distant galaxies, in the rocks of our own solar system, was hard to fit into a model where supernovae were the main source. There was also a deeper problem. To run a successful R process, you need not just energy and density. You need a specific kind of matter. You need it to be rich in neutrons, almost neutron pure, with very few protons. Most of what flies out of a supernova is not like that. Most of it has plenty of protons. The conditions inside a supernova explosion are violent, but they are not the right kind of violent. And there was a third problem, which was about timing. Astronomers studying very old stars in our galaxy found that even some of the oldest, simplest stars contained traces of heavy elements. That meant the heavy elements had to have been made very early, in the first billion years or so of the universe, which meant whatever process was making them needed to start producing material very quickly after star formation began. Some models had a hard time meeting this deadline. A few astronomers, starting back in the 1970s, began to suggest a different idea. What if the R process did not happen during a star's death? What if it happened during a collision? What if there were objects in the universe so dense, so rich in neutrons, that the only way to release their material into space was to slam two of them together? For decades, this idea was a footnote. The math was sketched out, but it was hard to confirm. Nobody had ever seen a neutron-star collision. Nobody knew, with confidence, how often they happened, or how much heavy material they actually produced. The supernova picture was the textbook picture, partly because it was the one that came first, and partly because the alternative seemed exotic and untestable. The math came up short. To understand what those astronomers were proposing, we need to talk about what is left when a massive star finishes dying. When a star much heavier than the Sun goes through its core collapse supernova, the explosion blows the outer layers into space. But the inner core does not get blown outward. It gets crushed in a way that is hard for the human mind to picture. The pressure becomes so extreme that protons and electrons are squeezed together inside individual atoms, and they merge. A proton and an electron, under that kind of pressure, combine to form a neutron. The whole structure of ordinary matter, with its little electron shells and its empty space and its precise atomic geometry, gives up. What remains is essentially a single atomic nucleus the size of a city. Just neutrons packed together, held up against further collapse only by the quantum laws that govern how closely particles can be stacked. This is a neutron star. A neutron star is what is left when a massive star fails. It is not a star in the way the Sun is a star. There is no fusion happening at the center of a neutron star. It does not glow because of nuclear burning. It is the corpse of a star, condensed into something almost geometrically perfect. The numbers are the part that the human mind never quite settles into. A neutron star contains a mass somewhere between about 1 and 2 times the mass of the Sun. The Sun, for comparison, is more than 100 times wider than the Earth. A neutron star is not. A neutron star is a sphere only about 12 to 20 kilometers across, about the width of a small city. Take more than the entire mass of the Sun, crush it into a ball you could drive across in 20 minutes. That is a neutron star. The density that comes out of those numbers is something you do not really feel, but the standard comparison is the one to hold on to. A teaspoon of neutron star material, brought to Earth, would weigh roughly 1 billion tons. Not metaphorically. Actually, the same teaspoon would weigh more than every car in a major city combined, more than every building on a mid-sized continent, more than the small mountain just outside whatever town you grew up near. Neutron stars also spin. Some of them spin many times per second. Some of the youngest known pulsars rotate hundreds of times per second, faster than any household appliance, despite being made of more matter than the entire Sun. Some of them have magnetic fields trillions of times stronger than the Earth's, strong enough that, near the surface, the structure of ordinary atoms would be twisted into elongated shapes. Some of them, called pulsars, send beams of radio waves sweeping across the sky like lighthouses, and we have detected hundreds of them. The surface of a neutron star is also strange. The crust, the outermost layer, is a thin shell of ordinary atomic nuclei pressed into a crystalline lattice harder than anything humans have ever measured. Just below the crust, the structure changes again. The atoms there have been so squeezed that the nuclei begin to fuse and deform into long shapes, sometimes called nuclear pasta, because the geometry, in computer simulations, looks like spaghetti and lasagna sheets layered together. Below that, the structure changes once more, into something even less familiar, and finally, at the core, into a sea of pure neutrons that physicists are still arguing about the exact behavior of. But in this story, the most important thing about a neutron star is not the crust or the pasta or the core's exact equation of state. The most important thing is what a neutron star is made of, on average. It is made of neutrons. That fact, simple as it sounds, is what makes a neutron star unique in the cosmos. Ordinary matter is a balanced mix of protons, neutrons, and electrons, with the electrons spread out in clouds around the nuclei. A neutron star has had most of its electrons crushed into its protons. What is left is almost pure neutron matter, vast, dense, neutron-rich beyond anything else in the universe except the very interior of a black hole. To run the R process and build the heaviest elements, you need an environment rich in free neutrons. There is no environment richer in neutrons than this. A neutron star is, in a sense, a galaxy stockpile of free neutrons, sitting frozen and quiet, waiting for something to release them. A teaspoon weighs 1 billion tons. If a neutron star is the densest, most neutron-rich object in the universe short of a black hole, then a system with 2 of them in orbit is the most explosive recipe nature has ever assembled. These systems exist. We have found dozens of them in our own galaxy. A binary neutron star system usually starts as a binary star system of 2 ordinary, massive stars. Both stars eventually exhaust their fuel. Both stars eventually go through their own supernova and leave behind a neutron star. If the original binary survives both supernovae, which is not guaranteed, what is left is a pair of neutron stars in orbit around each other. For a long time, that orbit can be quiet. The 2 neutron stars circle each other slowly, separated by millions of kilometers, moving the way the Earth moves around the Sun. Nothing dramatic, nothing apparently in motion at all. If you were somehow watching the system from a nearby star, with even the most powerful telescope, you would see 2 faint points of light, very close together, doing essentially nothing. The 2 corpses would seem stable. They would seem permanent. They would seem like an unchanging feature of the local cosmos. But because they are neutron stars, and because they are dense, they do something the Earth and Sun do not do, at least not in any noticeable way. They radiate gravitational waves. Gravitational waves are ripples in the fabric of space itself, predicted by Einstein and confirmed by direct measurement only in the last decade. Any 2 objects in orbit around each other emit gravitational waves. The Earth and the Sun emit them too, but at a rate so faint that even the Earth's orbit is barely losing any energy after billions of years. With neutron stars, the story is different. The masses are huge, the distances are short, the orbital speeds are fast, and the gravitational wave emission is significant. Energy slowly leaks out of the orbit, carried away by ripples in space. And as the orbit loses energy, the 2 neutron stars drift closer together. Then they drift closer still. The closer they get, the faster they orbit. The faster they orbit, the more gravitational waves they radiate. The more they radiate, the closer they get. It is a feedback loop with one inevitable outcome. There is no equilibrium. There is no stable distance. Once a binary neutron star system is in this state, it is on a one-way path. For most of these binaries, the path is incredibly long, hundreds of millions of years, sometimes billions. The 2 neutron stars dance slowly, almost imperceptibly drifting closer, while entire civilizations rise and fall on planets thousands of light years away. Whole species evolve and go extinct while the 2 corpses are still figuring out their final embrace. Eventually, though, the orbit shrinks enough that the dance becomes a fall. The last 100,000 kilometers go in seconds. The last few hundred go in less than a heartbeat. The two neutron stars collide. They cannot stop. They cannot slow down. For a long time, this collision was theoretical. We knew binary neutron star systems existed. We could measure how their orbits were tightening. We could predict, given enough time, that some of them would eventually merge. But we had never actually seen a merger happen. We did not know what one looked like. We did not know what it would leave behind. That changed on August 17, 2017. At 12:41 in the afternoon, Universal Time, a network of laser interferometers picked up a signal. Two of those interferometers were the Laser Interferometer Gravitational Wave Observatory, or LIGO, sites in the United States. The third was the Virgo detector in Italy. All three machines are designed to do one thing. They look for tiny stretches and squeezes in the fabric of space itself, the kind of distortion only a passing gravitational wave can cause. The signal that came in that day was not like anything they had picked up before. In the previous 2 years, LIGO had detected gravitational waves a handful of times. All of them had come from collisions between black holes. Those signals were brief. A short chirp, lasting a fraction of a second, as two black holes spiraled together and merged. But the signal on August 17th lasted much longer, about 100 seconds. It was a long sweeping chirp, rising in pitch as the source got closer and closer to merging, long enough for the data team to realize, in real time, that this was something different. The masses involved were too small to be black holes. They were in the right range for neutron stars. 2 seconds after the gravitational wave signal ended, NASA's Fermi Gamma Ray Space Telescope, in orbit around Earth, picked up a brief flash of gamma rays from the same direction. A short gamma ray burst. 2 seconds was the gap between the gravitational waves and the light. The world's astronomers spent the next 11 hours trying to figure out where, exactly, the signal had come from. The patch of sky was narrow but still large enough to contain many possible host galaxies. Telescopes in Chile, Hawaii, South Africa, Australia, and dozens of other places were all looking. Eventually, the Swope telescope at Las Campanas Observatory in Chile spotted a new point of light in a galaxy called NGC 4993, in the southern constellation Hydra. NGC 4993 is about 130 million light-years away. That is the distance from Earth to where these two neutron stars lived. Light from that galaxy, traveling at the speed limit of the universe, takes 130 million years to reach us. The two stars had been dancing around each other for roughly 11 billion years before the final fall. The last 100 seconds of that dance produced the signal we caught. The new point of light was not just visible in optical telescopes. As the days went on, it could be seen in infrared, in ultraviolet, in radio. Almost every kind of telescope on Earth, and several in space, ended up watching it. Over 70 observatories contributed. Thousands of astronomers became part of the same observation in real time. It is hard, even now, to convey how unprecedented that coordination was. Most astronomical events are observed by one telescope, then maybe a handful, sometimes by entire teams over weeks or months. This event, on the day it was caught, became the focus of essentially every observatory on Earth that could see that part of the sky. Group chats and email lists across continents lit up. Observation schedules were rewritten in real time. Astronomers who had never collaborated were suddenly comparing notes hour by hour. Years of theoretical predictions, made by separate teams over decades, were being tested in front of everyone simultaneously. What they were watching was the afterglow of the merger. A new word entered everyday astronomy that week: a kilonova. We had a front row seat. The kilonova was bright. At its peak, it was emitting about as much light as 200 million suns combined. But it faded fast. In the first day after the merger, the visible light was strong and blue. Within a few days, it had dimmed and shifted toward the red. Within a week, the optical light was almost gone, but the infrared emission was still there. Within 2 weeks, even that had begun to fade. By a month, the kilonova was a thin trace in the data. By a few months, it was effectively gone. That fading curve, the way the brightness rose and fell across different wavelengths of light, told astronomers what was happening inside the cloud of debris. Theoretical models predicted that if a neutron-star merger really did produce heavy elements, the cloud of new matter would behave in a very specific way. The lighter products of the R process, things like strontium and yttrium, would emit blue light first. The heavier products, the lanthanides and the elements near gold and platinum, would absorb that blue light efficiently. They would re-emit it in the infrared, and they would do so for weeks, not days. That is exactly what was observed. The light curve of the kilonova in NGC 4993 fit the theoretical predictions for our process nucleosynthesis almost perfectly. For the first time in history, we had directly seen heavy elements being made. The total mass of new heavy elements created in the merger has been estimated, from those observations, at about 16,000 times the mass of the Earth. Of that, about 10 Earth masses went into gold and platinum specifically. The rest spread across the heavy half of the periodic table. Lanthanides, tellurium, strontium, cesium, barium, a pinch of nearly every heavy element we know about. But the data was not perfect. The lightest products of the R process were clearly identified in the spectra. Strontium showed up directly. Some of the medium-weight lanthanides could be inferred, but evidence for the very heaviest elements, the ones around gold, platinum, and uranium, has been harder to pin down in this single event. The light from those elements is faint, and the spectra of kilonovae are dense and tangled. So we know, with confidence, that the merger produced heavy elements. We know, with confidence, that it produced a great many of them. The total mass yield is well constrained. The spectral signatures of light R process elements were clearly seen. But for some of the very heaviest individual elements, the case rests partly on theoretical models, filling in what the spectra alone cannot fully resolve. This is the kind of honesty the science demands. The discovery was real. The picture is mostly clear, but the picture is still being refined. Some of the heaviest elements left subtle fingerprints, and astronomers are still working through what those fingerprints mean. Some elements are still missing. To stay with what we know, walk back to the beginning of the journey. Light leaving NGC 4993 on the day of the merger started traveling toward Earth 130 million years ago. Not metaphorically. Actually, picture the Earth 130 million years ago. The continents are not where they are now. South America and Africa have just begun to drift apart. The Atlantic Ocean is a young, narrow sea. Dinosaurs are walking on every continent. The ancestors of birds are starting to glide between trees. The first flowering plants are appearing. Mammals are small and nocturnal, hiding in burrows. There is no human eye anywhere on the planet to see anything. The sky on Earth, on a clear night, would look mostly familiar. Many of the same constellations would be there, though slightly distorted. The sun would be the same sun. The moon would be the same moon, though its orbit was a little different. And in a small patch of southern sky, in a galaxy nobody could have known about, a faint flash of light began to leave a single point and head outward in every direction. For 130 million years, that light traveled. It traveled while the dinosaurs went extinct. It traveled while the first primates evolved, while the first humans walked, while every empire rose and fell, while every language was born. It traveled while the pyramids were being built, while ancient libraries were filled, while ancient libraries burned, while the printing press was invented, while every word ever written was written. The light kept moving. When it finally arrived at Earth in August of 2017, it found a world full of detectors that could read it. LIGO, Virgo, Fermi, Hubble, the Very Large Telescope, the Swope Telescope, networks of radio dishes, spacecraft in orbit, people in shifts, watching their screens ready. The reception was almost too perfect. A faint signal, 130 million years old, walking into a system designed exactly to catch it. If LIGO had not been built, the gravitational waves would have passed through us, and we would never have known. The Earth would have flexed, by less than the width of an atomic nucleus, in a way nobody could measure. The kilonova in the sky, faint and small from this distance, would have appeared as just one more transient flicker among countless others. By the time anyone pointed a telescope, it would already have faded. The catch was so close to being missed that part of the wonder of it is the timing. We finished building these detectors. We ran them. We caught the first one at exactly the time we were ready. 130 million years of precise travel, ending in a few seconds of recognition. And here's something to hold for a moment. Every time you stand outside under a clear night sky, the light from those stars is also old. Some of it is years old. Some of it is centuries old. Some of it is thousands of years old. The light from the most distant naked-eye galaxies, like Andromeda, is more than 2 million years old by the time it reaches your eye. Looking up is, always, looking back. But 130 million years is a different scale of looking back. That is roughly the age of the oldest dinosaurs in the fossil record. To see this kilonova was, in a sense, to receive a message from a time before any creature on Earth could have understood the message. It was a piece of information that had been in transit since before the brains capable of reading it had evolved. And the matter that came with that information, the cloud of gold and platinum and lanthanides, is still expanding. The light reached us in a flash. The matter is moving slower, but it is moving. It will not arrive at any specific destination. It will simply continue to expand and dilute and eventually merge with the gas of its host galaxy, where, in a few 100 million years or a few billion, some of it will end up in new stars and new planets in NGC 4993, somewhere on a planet that does not yet exist, in a future that has not yet happened. That matter will be part of the floor of an alien sea, or the air of an alien sky, or the bones of an alien creature, just as the matter from earlier collisions in earlier galaxies ended up in our own. And then the light was gone. The light started before humans could write. Now think about what that light, and the matter that came with it, leaves behind. After the merger, the cloud of new material expanded outward into the space around NGC 4993. It moved fast. The ejected matter from a kilonova is launched at a meaningful fraction of the speed of light, depending on the angle and the mechanism. For the parts of the cloud moving more slowly, the speed is still tens of thousands of kilometers per second. For the faster parts, the speed approaches a quarter of the speed of light. 16,000 Earth masses of new heavy material, fanning out into the surrounding galaxy. This material does not stay in a single neat shell. It mixes with the existing gas and dust of the host galaxy. Over millions of years, it spreads and thins, distributing itself across many cubic light-years of space. The cloud becomes part of the diffuse interstellar medium. Eventually, in some places, that gas is dense enough to begin to gather under its own gravity. When gas gathers under its own gravity in interstellar space, it forms new stars, and around those new stars, dust and ice and rock can clump into planets. This is the central insight that turns this story from a violent astronomical event into a personal one. Every atom of gold or platinum or uranium that you have ever heard of, anywhere on Earth, was once part of a cloud like the one ejected by GW 170817. Not necessarily that one, but events like it. The Sun and the Earth formed about 4.5 billion years ago, out of a cloud of gas and dust that had been enriched over the previous several billion years by countless prior stars and prior collisions. That enriched cloud carried hydrogen and helium left over from the Big Bang. It carried carbon and oxygen and iron made by ordinary stars, and it carried a thin scatter of heavier elements, gold, platinum, uranium, mercury, lead, made in the violence of dead stars merging and dead star cores, tearing themselves apart in extreme events. When the sun ignited in the middle of that cloud, it pulled most of the hydrogen and helium toward itself. The leftover dust, the rockier and metal-rich material, settled into the protoplanetary disk and eventually became the rocky planets. Mercury, Venus, Earth, Mars, Earth in particular, ended up with a generous helping of those heavy elements baked into its early structure. Most of the gold and platinum that was originally part of Earth sank into the core during the planet's molten youth. Iron sank too, dragging much of the heavy material with it. The crust and upper mantle, which is where humans actually live and dig, would have very little of these elements left, except for one further accident. After the early Earth had differentiated into core, mantle, and crust, additional heavy material rained down from later asteroid impacts. That rain of late impacts is what put most of the accessible gold and platinum into the surface layers we can mine today. So when humans dig a gold mine, They are not actually reaching down into the original gold of Earth's formation. Most of that original gold is unreachable, locked in the iron core, thousands of kilometers below any drill humans have ever made. The gold that is actually mined is the much smaller fraction that arrived later, on the backs of asteroids, after Earth's surface had already cooled enough to keep it from sinking. Humans have never touched the bulk of Earth's heavy element inheritance. They have only ever touched the leftovers from a second delivery. So the gold in the wedding ring on someone's hand right now has a long history. It was made originally in something like the GW-170817 collision, perhaps several different events over billions of years. It drifted in space. It joined a cloud. It was incorporated into the early solar system. It became part of Earth. It sank into the core. And then, after Earth had cooled, a second generation of asteroid impacts brought another supply of similar atoms, raining them onto the new crust, where they would stay close enough to the surface for humans to eventually find 16,000 Earths worth of new matter. So now look at your own room again. Look at your phone. Look at the metallic edge of any device near you. Look at your hands, with whatever rings might be on them, or just the bare skin if there are none. Look at the back of a watch, or at the connector port on a charging cable, or at any small piece of electronics on the desk or shelf in front of you. The thin layer of gold inside the connectors of your phone was made in a kilonova, not your phone's gold specifically traceable to GW-170817, but gold made by the same kind of process in some collision long before the Earth existed. Those connectors carry signal because gold is one of the best conductors that does not corrode. The reason it does not corrode is something specific to its atomic structure, and that atomic structure exists because, billions of years ago, two neutron stars somewhere collided and threw a cloud of new matter into space. The platinum in catalytic converters in cars came from the same kind of event. Platinum is rare on Earth precisely because most of it sank into the core. What is left in the crust is the little that was delivered late by asteroids, after Earth had already cooled. Every gram of it began in a neutron-rich explosion in some galaxy, in some era, that we will never know. The uranium in nuclear reactors and in atomic weapons, the heaviest naturally occurring element, came from the same kind of event. Uranium is one of the heaviest products of the R process, and the R process essentially does not run anywhere except in extreme environments like neutron star mergers. Every fuel rod, every isotope, every measurement of natural radioactivity in old rocks ultimately points back to a violent collision somewhere in the deep past. Mercury in old thermometers, the heavy gray liquid metal you may have seen as a child, came from the same kind of event. The iodine that your thyroid needs to function, the trace iodine in salt and seafood that keeps your metabolism stable, was made in the same kind of event. Your thyroid, a small gland at the base of your throat, is quietly using atoms forged in a dead star collision to keep your body running. The tellurium in solar panels, the bismuth in some medications, the rhenium in jet engine blades, the rare earth elements in your phone screen, and in every wind turbine ever built, all of it came from the same kind of event. You do not contain very much of this matter by mass. Your body is mostly water, mostly oxygen and hydrogen, mostly carbon, all of which came from ordinary stars. The heavy stuff in you is a trace amount, a scatter of iodine, a bit of zinc, a few grams of trace metals. Your body is, in mass, mostly an old star body, but your environment is not. The hardware of modern human life depends on the heavy half of the periodic table in a way ordinary stars cannot account for. Take it away, and the lights go out. Take it away, and electronics stop working. Take it away, and modern medicine quietly stops being able to deliver many of its treatments. Take it away, and the chemistry that runs civilization would have to be rebuilt from scratch with a much shorter list of ingredients. You are surrounded by it. You hold it in your hand. You carry it in your pocket. You wear it on your finger, sometimes. You sleep in a building whose wiring depends on it. You breathe air filtered by it. You charge a phone whose connectors are coated in it. You drive past lampposts whose bulbs use it. You walk into rooms whose smoke detectors carry traces of it. You cross bridges held together by alloys that depend on it. You eat from utensils that may contain it. You sit on furniture in a house, in a city, in a country, in an economy, that has been built on the quiet foundation of these heavy elements. And every gram of every one of them was made somewhere violent. You are wearing the wreckage. There is something strange about realizing this. The places in the universe that are most violent, the most extreme, the briefest, are also the places where the most precious things are made. Not metaphorically precious, literally precious. Gold and platinum and uranium are precious because they are rare. They are rare because the only places they can be made are unusual. They are unusual because the conditions required to make them, dense neutron-rich matter, energies above what any normal star can produce, brief moments of geometry that nothing in human experience compares to, only exist in the depths and collisions of the densest objects in the cosmos. The sun, for all its size and warmth, cannot make gold. The sun is not extreme enough. To get gold, the universe needs something that has already given up being a star, something that has finished, collapsed, and become as compact as matter is allowed to be without becoming a black hole. Then it needs another one of those things. Then it needs them to spend 1 billion years drifting closer. Then it needs them to fall together and tear themselves apart. A neutron-star merger is, in some sense, a kitchen. The kitchen does not run for very long. The whole event, from the final inspiral to the dispersal of the ejecta, takes minutes to days, depending on what you count. The actual R-process synthesis happens in a fraction of a second. The decay cascades that turn that brief synthesis into the final stable elements happen over hours and weeks. By the time the kilonova fades, the kitchen is closed. The cooks are gone. What remains is a black hole or a single, more massive neutron star, and a slowly expanding cloud of new matter drifting outward. The kitchen produces the heaviest atoms in the universe. The kitchen produces them by tearing itself apart. There is no peaceful version of this process. There is no calm star anywhere in the cosmos, slowly building gold over billions of years. That is not how the universe works. The recipe requires destruction. The recipe requires that two corpses fall into each other and shatter. The recipe requires that the conditions for synthesis exist for less than a second. If you wanted to design a universe where gold was easy to make, you would not design this one. You would build something where ordinary stars could keep climbing the periodic table without limit. You would let the slow, steady process inside an ordinary star produce a thin trickle of every heavy element, distributed evenly through every galaxy, available everywhere in roughly the same amount. That universe would be simpler. It would also be less interesting. The heavy elements in that universe would not be precious. They would be common. In our universe, they are not common. They are the leftovers of rare, brief catastrophes. They exist because, every so often across cosmic time, two of the densest objects in existence fall together and produce a flash of synthesis that nothing else can match. The rarity of the events is what makes the elements rare. The violence of the events is what makes the synthesis possible. The timing of the events is what determines which volumes of space end up enriched and which volumes stay simple. And yet the result, the gold in the wedding ring on someone's hand right now, is some of the most stable matter on Earth. Gold does not rust. Gold does not tarnish. Gold can sit untouched for thousands of years, in a sealed tomb or a sunken ship, and emerge looking the same. The most violent process in the universe produces some of the calmest matter in existence. It is a strange inheritance. Atoms born in a fraction of a second of nuclear chaos, then sitting quietly, almost indestructibly, for 10 billion years. Atoms that record by their very existence the fact that something extreme happened somewhere, long ago, and that the something extreme cooled and settled and became, eventually, ordinary. The kitchen is small. The kitchen is violent. There is a careful caveat to add before we move on, because this story is still being refined. It is now well established that neutron-star mergers produce R-process elements. GW 170817 confirmed that directly. It is also well established that they produce a great many of these elements. The yield estimates from that single event, 16,000 Earth masses of heavy material, are robust. What is still being argued about is exactly what fraction of all the heavy elements in the universe comes from neutron-star mergers, and what fraction comes from other rare events. The strongest competitor to neutron-star mergers, in current research, is something called a collapsar. A collapsar is a special kind of supernova. When a particularly massive, rapidly rotating star collapses into a black hole, the collapse can launch jets of neutron-rich material. Some researchers argue that those jets, and those rare events, are responsible for a significant portion of the universe's heavy elements. Maybe most of them, in some models. This is a real disagreement in the field. Some teams analyze the elemental abundances in old stars and conclude that neutron-star mergers are too slow and too rare to account for the heavy elements seen in the very oldest stars in our galaxy. Other teams argue that the merger rate was probably higher in the early universe, and that mergers can plausibly explain those abundances after all. The honest summary is that neutron-star mergers are confirmed as a major source of the heaviest elements. They may be the dominant source. They may share the work with collapsars and possibly with other rare extreme events that are not yet fully understood. The careful claim is that GW170817 settled one half of the question of whether neutron-star mergers can produce significant heavy element yields. The other half, the question of how the cosmic budget for heavy elements is divided across all possible sources, is still actively being studied. Future detections will help. LIGO and Virgo have continued to observe, and other detectors are joining the network. The hope is that, in coming years, more neutron-star mergers will be observed in detail, and the spectra of their kilonovae will reveal more about which heavy elements are produced and in what proportions. Any single event leaves a partial fingerprint. A collection of events, observed across many galaxies and many distances, would give a much fuller picture of the cosmic chemistry. This is how science actually moves forward. A big question gets split into smaller pieces. Some of the pieces get answered. Others stay open. The picture gets clearer in places and stays fuzzy in others. The answer to where heavy elements come from is not a single tidy sentence. It is a list of contributing processes, with different fractions estimated by different research groups, and the fractions themselves still being measured. What is not in doubt is that the ring on a finger, the connector in a phone, the rod in a reactor, was made somewhere extreme. The fingerprints are unmistakable. Whether it was a merger like GW170817, or a collapsar, or some combination, the event was rare and brief and unimaginably violent. We do not yet know the recipe. There is one more thing to sit with before the closing. The two neutron stars that merged in NGC 4993 had been in orbit around each other for something like 11 billion years. 11 billion years. That is not a typo. The universe itself is only about 13.8 billion years old. These two stars had been orbiting each other for most of the history of everything. Picture what that means. Both of those stars used to be ordinary, massive stars, probably during the first generation or two of star formation in the universe. They burned through their hydrogen, their helium, their carbon, their oxygen. They reached the iron wall. They collapsed. They exploded as supernovae. Each of those events lasted weeks at most, and then the corpses settled into orbit. Two neutron stars, dense and cold and dead, drifting around each other in the outskirts of a galaxy that was itself still being assembled. Around them, in the early universe, the first big galaxies were merging into the structures we know today. Stars were forming and dying in nearby regions. Planets were beginning to coalesce around some of those stars. Maybe life was beginning, somewhere, on some of those planets. Maybe whole histories rose and fell on worlds we will never see. And the two neutron stars, in what would eventually be called NGC 4993, just kept orbiting. They kept orbiting while the Earth had not yet formed. They kept orbiting while the early sun was still gathering itself out of a different cloud of gas and dust. They kept orbiting while life on Earth started in tide pools, while it diversified into all the things that live in the ocean, while it crawled out onto land. They kept orbiting through every dinosaur. They kept orbiting through the asteroid that killed the dinosaurs. They kept orbiting while mammals took over the Earth, while humans emerged, while the first fires were lit, while the first cave paintings were made. For most of that time, nothing about the orbit looked dramatic. The two stars were moving slowly, by cosmic standards. They were millions of kilometers apart. The energy bleeding out of the system as gravitational waves was a tiny trickle, barely detectable to any imaginable instrument. If you had been watching from a nearby planet, the two stars would have looked almost still. But the trickle never stopped, and that meant the orbit, even when nothing seemed to be happening, was always shrinking. Always. Imagine standing in front of an enormous clock with a single moving hand, and the hand is so slow that you cannot see it move. You stand for an hour, and you cannot see it move. You stand for a day, and you cannot see it move. You leave, and your children come back to the same clock, and even then, the hand is barely shifted. But across many lifetimes, the hand makes its journey. The orbit of those two neutron stars worked the same way. No single human lifetime would have noticed any change. No single civilization would have noticed any change. But across geological time, the hand was always moving toward the bottom of its arc. The last few thousand years of the orbit went faster. The last few months, faster still. The last hour was a blur. The last minute, an unraveling. The last second, a collapse. The last 100 milliseconds, a collision so geometrically perfect that LIGO, on a small water-covered planet 130 million light-years away, would later read it like a piece of music. The whole 11 billion years of slow approach compressed itself into a final 100 seconds of audible chirp on a detector that had been operating for, in human terms, an eye blink. 3 days before, the detectors had been recalibrating. 3 days after, they would be back in routine operation. The window of recognition was narrow, and the signal walked right into it. The two stars themselves, in their last moments, would not have known they had been seen. They would not have known there were any creatures anywhere in the universe capable of seeing them. The collision was not for anyone. It was just the inevitable end of a slow, indifferent process. The fact that it ended up being recorded by us, in our generation, was an accident of cosmic timing that none of the participants could have anticipated. And yet here we are, sitting somewhere on Earth, hearing the story of it. 11 billion years of slow falling. So now pull all of the threads together. Every wedding ring contains atoms that were made in something like that. Every gold filling, every gold-coated connector inside every electronic device, every wire that depends on rare metals, every reactor rod, every old thermometer, every catalytic converter, every solar panel using tellurium, every magnet using rare earth elements, every car battery using lithium derivatives, every old painting whose pigments included heavy metals. All of it came from somewhere violent. All of it came from somewhere brief. Some of it came from neutron star mergers, like GW170817. Some of it came from collapsars, the rare giant stars whose deaths involve jets of neutron-rich material being thrown into space. The exact fractions are still being measured. The general truth is not. The heavy half of the periodic table was forged in places where the universe ran out of normal options, where ordinary stars could no longer build. Something unusual had to step in, and whatever stepped and did so briefly, in a fraction of a second of synthesis, surrounded by hours and days of decay, all of it followed by millions of years of drifting and dispersal. That is how heavy matter gets distributed across a galaxy, not in an even snowfall, in rare loud events scattered across cosmic time, each one seeding a small region with new ingredients. Most stars never benefit. Most regions of space remain mostly hydrogen and helium and a thin scatter of medium elements. Only the lucky volumes, the ones that happen to be near a neutron star merger or a collapsar in their formative age, end up rich in the truly heavy stuff. Earth was one of the lucky volumes. The cloud of gas and dust that became our solar system 4.5 billion years ago had been seeded, somehow, somewhere, by enough rare events to give it a thin coating of gold and platinum and uranium. Not a lot. Most of Earth is still iron and silicon and oxygen and ordinary lighter elements. But just enough heavy stuff to fill a periodic table. Just enough to leave gold for early human civilizations to find. Just enough for a few grams of platinum to end up in a catalytic converter on a quiet street tonight. It is, when you slow down to look at it, a long inheritance. All of it scattered. So here is the paradox at full weight, restated one last time. The heaviest, rarest matter you will ever encounter, in any form, was forged in events that lasted a fraction of a second, in conditions that exist almost nowhere in the universe, during the violent collisions of objects that have already finished being stars. Two corpses, falling together for billions of years, ending in a flash that we caught for the first time in 2017. The matter that came out of that flash is now scattered across galaxies. A small portion of it eventually found its way into the early solar system, into the early Earth, into the rocks that humans dug up, into the ring on a finger, into the wire in a wall, into the connector in a phone, into the trace metals in a body. You can hold an object in your hand right now whose atoms were stable for more than 10 billion years inside a corpse star. Then they spent a few hundred milliseconds being battered out of that corpse in the most extreme nuclear physics the universe ever sees. Then they spent another billion years drifting through space. Then they were caught up in the formation of a new solar system. Then they spent more billions of years inside the Earth. Then a human, or many humans across many generations, dug them up, refined them, shaped them, and put them where you are now seeing them. That history is sitting in the room with you tonight. Old, quiet, heavy, yours. The universe builds most things slowly, in stars, over millions of years. But once in a long while, it does something else. It takes two corpses, presses them together until they shatter, and produces a cloud of new matter so violent and so brief that we have only ever seen one of them in detail, and we had to spend decades building the right machine to catch even that. The matter that came from that one event, and from countless others like it, is in your room. It is in the clothing you might be wearing if any of it has any metallic thread. It is in the building around you. It is, in quiet trace amounts, inside the body resting under whatever you have pulled over yourself tonight. You do not have to do anything with this. You do not have to remember the numbers. You do not have to remember the date, or the galaxy, or the names. You are not being given a task. You are being given a small, quiet fact to hold for a moment before you sleep. The heaviest things in your life were forged in the universe's smallest, densest, briefest depths. And then they made their way slowly, across an unimaginable amount of time, into your hands. That is enough for tonight. Good night.